Tu albo tu. Czy tu leżała taka torba?
A skąd wyciągasz?
Było z tej torby.
A.
Dobra.
We will continue the morning session. In this part, it will be only one plenary lecture. And before this lecture, I want to remind you that after the lecture there is a lunch, and lunch is exactly the same place as coffee break. Now the lecture will be led by Stefan Jackowski from University of Warsaw, and I give him the microphone. Continue.
Thank you. It's a great honor and pleasure to introduce the first plenary speaker, Aleksy Tralle. Aleksy, please, floor is yours. Well, I would like to present him a little bit. So he was born and also mathematically in Minsk, in Belarus, and then moved to Poland. Since the beginning of his career, he is interested on interaction of differential geometry and topology. I like very much this kind of mathematics, so it's even bigger pleasure to introduce him as a speaker. He is now professor at the university in Warmia, Mazur. It's called. It's in Olsztyn, in northeast of Poland. He also is an active member of our society. He served on the executive board of the society. He organized various conferences. So I really appreciate Alex's contribution to mathematics and to our society, and I'm sure you'll enjoy Sasakian structures on some Smale-Barden manifolds after his talk. The floor is yours.
Thank you very much, and thank you very much for this warm introduction. Really, the title of my talk is Sasakian Structures on Smale-Barden manifolds. It might be look a bit specific, but nevertheless, there is, I believe, interesting and quite general mathematics behind this. I'm a bit nervous, and I feel very honored to be here and to present this talk to some distinguished audience. So the kind of justification for this is that my more than 20 years collaborations with my Spanish co-authors and friends, with gratitude to them. So it's in chronological order with people with whom I published papers. So Raúl Ibáñez, Luis Ugarte, Marisa Fernandez, Vicente Muñoz, Juan Ángel Trabajo Carulli, and Alejandro Cañas. So here is, say, my friends, my big friend Raúl, Vicente, Marisa, Juan Ángel. So, and now let me begin with some simple thing, but it should be somehow notation should be fixed. So let us look at contact forms first. So we have an odd-dimensional manifold. Well, basically we would like, of course, to consider it closed, but for the moment it will be just odd-dimensional manifold with a contact form. So contact form means what is written here. So the wedge product is, then it's a form of 2n plus 1 degree, and it is not 0 everywhere on M. And then you can immediately see that then there is a vector field psi, which is called the reg vector field, which is defined by these equations. The sign means that it is a contraction. These are tensors, so it's just a contraction of tensors. And psi determines a one-dimensional foliation, which is called characteristic foliation. And then, of course, you get the decomposition of the tangent bundle to the D, which is to n, so even dimensional distribution, and then the tangent to this vector field psi to this foliation. So maybe just for getting some feeling what may happen, consider this the most simple case. So it's just odd-dimensional Euclidean space with fixed coordinates x1 to xn, y1 to yn, z. And then if you define the differential form by this formula, which you see, then you can just calculate the wedge product, and you will see that then really this form is non-vanishing everywhere. The second example may be a bit more complicated, because if you take a sphere that in the even dimensional Euclidean space, usual, say, one sphere of radius 1, then you have coordinates x1 to x1, x0, xn to y not yn. And then if you write down this form and restrict it to the even dimensional sphere, then of course x and y satisfy additional restriction, and due to this restriction, when you calculate the wedge product, you will get something which is written. Then to show that this form never becomes 0, you need extra calculation. You should take the differential form, which is written, of course, there are, say, this bracket is not necessary. And then you can check that if you calculate beta wedge product with this form, then you get something. And then you use the condition that if you restrict this on the sphere, then it cannot be 0. So also this form eta wedge d eta to the nth power also cannot be 0 everywhere. Can be 0 at some point. So this means that you get what you want. And so this definition is somehow technically complicated, and of course it doesn't look very nice. But it's not true. It's nice. It's a right definition for Sasakian structure. So what does mean Sasakian? So you have a contact manifold. You begin with contact manifold, but then you want to do something to get it Riemannian, to have not only a compact structure, but you want to have some compatibility with Riemannian metric on the manifold. And then the formal definition, which I will try to explain less formally in the sequel. So we say that the contact manifold M eta, that means a Sasakian structure, and then we say the huge geometric structure. So you have manifold, Riemannian metric, reg vector field, contact form, and some 1-1 tensor J, and such that this endomorphism J satisfies some identities. When you square it, you get this matrix, so in fact, yes, minus identity, and this extra term, yes, so it is not an almost complex structure. If it were almost complex structure, you would get j squared equals to minus identity. But then you add additional tensor, psi tensor with eta, so it's a tensor of type 1, so it's a matrix. And then you demand that d eta is compatible with j, so it's this relation. The third relation is that psi is a Killing vector field. So with respect to Riemannian metric, which is also determined. It's determined by this formula. You can first check that it's a Riemannian metric. And then it is Killing, so the Lie derivative of this metric is 0. And then you can, you need to do some more extra structure. You take the contact cone, so it's Israeli cone, with Riemannian metric, which is a word product, so it is t squared. If t is a coordinate in real line, half line in fact, then t squared g plus d theta squared is defined by, you have this contact cone, which is written, and then you define a new tensor, which I denoted by I, and then it is j on the distribution d. If you remember, it's the kernel. It's just the kernel of the differential form eta, and then you just put I of xi. It's this vector field, and I of the other vector field is minus psi. So it's obvious that it is an almost complex structure because I obviously satisfies this this identity I squared equals minus identity. But then, if you want to get this moment, you can stop and say that you have a so-called K-compact structure. I even didn't write the definition of this. But if you demand that this is integrable, then we get the formal definition of a Sasakian manifold. So it's a contact manifold with some compatibility Riemannian condition. Okay. So maybe it is better, instead of just looking at the formal definition, maybe it's better to think over how to think about Sasakian manifolds. What is it? So there's example which is easy to understand. It's so-called Boothby-1 bundle. What is it? If you take just even dimensional x omega, which is just a symplectic manifold, so it's just a symplectic formula, and you also demand that the cohomology class of this symplectic form is integral. In this case, you just take a principal circle bundle determined by this omega. And then it's just a Chern class of this circle bundle. And then you have a theorem, which I will try to explain in say, more informal terms. The theorem is that the Boothby-1 circle bundle admits a K-compact structure. But if you demand that x omega is scalar, then the total space M will be Sasakian. And then it is easy to think about Sasakian manifolds in this context. Just say, look at Hopf bundle, yes? So if you look at Hopf bundle, you get, a toy example of Sasakian structure. Then, yeah, well, it's clear, yeah, that if you get the Hopf bundle, then it is determined by the Chern class of CP1, CPN, so in general, CPN. So, of course, to get this bundle, maybe somebody will need to explain explanation. So S1 acts on S2 and plus 1 just by multiplication. So you can think about Hopf bundle. It's a very good way of thinking about about Sasakian manifolds, and in particular, Boothby-1 circle bundle is a toy example of Sasakian structure. How to somehow to understand this? Maybe it will be somehow helpful to make some explanation, which also is somehow, there are many references, unfortunately. One ingredient to look at this is the so-called Kobayashi theorem, which I will not prove. It's a quite involved local argument, but Kobayashi's theorem proved in the 60s and 20th century is that there exists a connection form, eta, on M, such that if you pull back this symplectic form, you will get exactly d eta. But then it means that eta becomes simultaneous. It's a connection form, but it is a contact form because d eta is non-degenerate on the horizontal distribution. And so, using this Riemann vector field, you can define a Riemannian metric in a way to get a Riemannian submersion. And because it's a Riemannian submersion, it has totally geodesic fibers. And then it means that the linear derivative is zero. So it's a Killing vector. And the integrability, it is not trivial to show. I can refer to, say, a very involved book by Boyer and Garnitsky. But you can check the integrability by some non-trivial calculation of the Nebenhuis tensor. So you just take your I, which was defined, and calculate this. Painfully calculate this, and you will many pages, and you will get this. So it's integrable if you take X as scalar manifold. So finally, Budwig examples give us a kind of explanation what is Sasakian manifold, and then we would like to get some more general case. So general Sasakian manifold. For general Sasakian manifolds, you can surprisingly you can somehow just generalize in a maybe non-easy way, but generalize the previous example. For this, you have something which is called Rukhin-Bira theorem. So the Rukhin-Bira theorem is, if a manifold admits a Sasakian structure, it also admits a so-called quasi-regular Sasakian structure, which will be described later. I will just say that quasi-regular is the same as Seifert bundle over Kähler orbifold determined by orbifold Kähler class. So on one hand, of course, everything looks very technical and it's really non-easy, but when you think about this, you can, on one hand, you have a fiber bundle, which is easy object, and then you somehow generalize this to make this construction more flexible. But what is, if you take orbifolds instead of manifolds, and Seifert bundles instead of fiber, say smooth fiber bundles, you get enough flexibility to solve problems in Sasakian geometry. And if your problems are in topological framework, then you can have everything. So it was, for me, it was a big surprise when with the help of my colleagues, especially Vicente Muniz, when I understood what is orbifold. Then I understood that this is somehow the right way of thinking about Sasakian manifolds. And so, what is our aim? I mean, the aim of my talk. Well, I will present a series of my works with Vicente Muniz and Matthias Schult, and the aim of this let's say, series of works was to create a reasonably general theory of Seifert bundles or Kähler orbifolds and use it to solve some existent problems in Sasakian geometry. I want to say that interesting mathematics in this area is when you try to prove the existence of the structure which I was defined. Because Kohler, the foundational works of Kohler, showed that there are very subtle obstructions to the existence of Sasakian structures, even in dimension 5. The first interesting dimension is 5, and then there are really very subtle obstructions described in some, say, complicated algebraic expressions in the second homology group of the manifold. And then they are very subtle. So it's not always clear what is it and where and when Sasakian structure does exist. So this was my somehow most main motivation for looking at Sasakian manifolds. So then just to be in order, yes, some advertising of Sasakian geometry. Some reasons which I have chosen in random because if you want to have the more examples of usefulness of Sasakian geometry, you should maybe consult the seminal book of Boyer and Galitsky, which is also entitled Sasakian Geometry. But there are some chosen at random reasons. First, if you take this Sasakian manifold, you have a tool to construct so-called eta-Einstein matrix. Eta-Einstein matrix is a generalization of the usual Einstein matrix, because you impose a condition on the Ricci curvature of the metric. If you have mu equals 0, then you get the Einstein matrix, but in general you have this so-called eta-Einstein matrix, and this is a kind of transversal, as they say, transversal theory. Quasi-regular Sasakian structures also is a tool to construct true Einstein matrix, and even Sasaki-Einstein matrix, and every simply connected Sasaki-Einstein manifold admits a Killing spinor. This is a Friedrich-Kapp theorem, and all this has application in mathematical physics, for example, in general relativity, supergravity theories, and supersymmetry. But of course, I don't want to pretend that I understand all this. It's just chosen at random applications. But because of that, I will conclude by saying that the existence problems for Sasakian structures yield interesting mathematics. And because of this subtle Culver's obstruction, among other examples. So what I want to do now is concentrate on, so this was kind of introductory part. Then orbifold. Well, I will give you formal definition, although maybe it is not very helpful and very instructive. But nevertheless, well, if you look at the definition of manifold, then you slightly change the definition. So now you just say that X is a Hausdorff paracompact with an atlas. But the atlas consists of some UI, which are of course open in the Euclidean space. But then you have also an action of a finite group GI, which acts linearly on this open sets UI. And then you have a projection, and your atlas on X consists of these projections, so UI, which are UI tilde divided by gamma, and of course this map phi is not the equivalent in a sense. Yes, so phi of gamma acts on the points of Euclidean space, and you get this one, and then of course you have an open cover, so X needs this open cover, and UI are open in X. And then you need some compatibility condition, somehow resembling the compatibility condition for charts on manifold. This is a formal definition, so for each intersecting charts constituting this atlas, you have also a chart which is in this intersection, and you have, of course, this covering, and then you have continuous maps of this type which commute with the action with your subgroups or groups gamma k and gamma I. And then, well, I won't go into this in more details because I will concentrate only on Smale-Barden manifolds. These are 5-dimensional manifolds. Because of this, I will consider only cyclic four orbifolds. And then if you consider cyclic for orbifolds, then your charts can be considered as C2, and we consider only one group, Z M. So the cyclic group of order M, which of course can be then considered here as a subgroup of unitary group. And then this is the action psi of Z1, Z2. It's just so locally, your action looks like the last formula on this slide. You have also a condition that the greatest common denominator is 1. Then maybe it's more instructive again to look at examples. So if you take any manifold and just take one group, gamma, which acts properly discontinuously, but not freely. If you want to have a true orbifold, then you want to say that your gamma doesn't act freely. But then there is, each point has finite isotropy, and because of the properly discontinuous action, you get this condition, which means that UP, which UP tilde divided by your subgroup, yield an orbifold atlas on this vector space m divided by gamma. And then it's an orbifold. So if gamma were acting freely, then you would get a manifold. But if your gamma doesn't act freely, then you have an orbifold atlas. It's an orbifold. And the other example, if you take a Riemann sphere, and then you just write the formulas for the atlas. SR2 consists of two charts. And then again you get an example of an orbifold. And then also let me say that very roughly I will try to say that orbifolds you can define geometric structures because you can define tensors. Then geometric structures defined by tensors can be, of course, somehow defined on orbifolds. So if you take an orbifold with orbifold atlas, then orbitensor is just a collection of tensors locally on each chart. But of course, then you just introduce more condition that they should be invariant with respect to the groups gamma I. And they agree on intersections. So it's just like a manifold, but you take the invariance condition into action. And then, because of this, if you can define tensors, then you can define orbidifferential forms, you can define orbi-Riemannian metrics, you can define orbi almost complex structure, and orbi-Kähler metrics. Definition is formally the same, yes, but you remember that now you have orbifolds, and these conditions must be invariant with respect to the group action. So these are geometric structures on orbifolds. Again, to speak about Sasakian manifolds and especially about existent problems, I need some terminology. So on orbifolds, you define your points into regular points and singular points. So if all points were regular, you would get a manifold. But there are singular points. So what may happen? Of course, the order of your group is called, of your isotropy subgroup, is called the order of the isotropy. And if we consider four orbifolds, all points of X are divided into regular. It means that there is no isotropy, so M of X equals 1. Isolated singular isotropy points, so it may happen that your point where M of X is not 0, but it might be singular and may be isolated. And also, it may be a surface, or if you think in a complex case, a curve, a singular curve with multiplicities. We call the order of isotropity multiplicities of these curves. I denote these curves by GI, and then you can see that this isotropy is just one MI for each DI, but these are just curves in a, say, complex two-dimensional orbifolds. These are curves. Or if you want, you can say in four-dimensional orbifolds and their surfaces. If you neglect the Kähler or complex structure. So let us, it is important for me, so let us fix a bit what types of local models are for four orbifolds. On one hand, it's easy, but nevertheless, I did not write up all possibilities. But just for example, your action maybe always looks this way, psi x on two complex numbers, just by this kind of multiplication. But then to make everything work, you need to consider conditions on the greatest common denominator. So they should be somehow mutually prime or what else. So these are formal conditions which you can see. And then depending on conditions, you can get either if greatest common denominator is 1, then look, then of course it means that if you take psi to the g1 power z1, psi to the g2 z2, it never equals z1 z2 except 1 point. So it's exactly the situation when you have a singular point, which is isolated, and the quotient, then if you look at the quotient, c2 divided by cm with m1 and m2 equals 1, then it means that it is an isolated singular point. It's certainly singular. But then you can get another possibility. For example, it's not all possible, but this possibility, let us look. M1, M2 greater than 1, D equals 1, then M must be M1 times M2, and then the M action on C2 is equivalent to the product action. But then it's homomorphic to C times C. So in this case, you get smooth points. It is called smooth. So your chart is just the same. It's homomorphic to C times C, to C2. So, but in this case, you get non-isolated fixed point, because then you have transversal to surfaces, D1, which is just locally Z1, 0, and D2, which is 0, Z2. So because of this, we divide points into non-smooth type, which is 1, and smooth points. Smooth points is type 2. So there are more possibilities, but they fall into smooth and non-smooth cases. And so we now will concentrate, because of course it makes no sense to go into technicalities, so let us concentrate on smooth orbifolds. The formal definition of smooth orbifold is that we say that a singular point x is smooth if U is homomorphic to a ball in R4. So it's exactly the previous slide, yeah? When I showed that it is C times C then. And then we analyze this case in more detail in my work with Rocha, Muniz, and myself. And so how we can look at smooth orbifolds. So let X be a smooth-oriented 4 manifold. Just take the manifold, but then do something else. Assume that we have some pattern of embedded surfaces in the eye, intersecting transversally, like on the previous slide, and with these coefficients, so with multiplicities mi greater than 1, such that they are mutually prime if the surfaces intersect. Then there exists a smooth orbifold structure, an orbifold structure on X with isotropy surfaces di of multiplicities mi. So you see that somehow what we do, we just distort the smooth structure to get orbifold. And even this construction gives us enough flexibility to solve problems, which we could not solve using bundles. But because this pattern of surfaces, which is just a kind of distortion of a smooth structure, we get what we want. And so the proof, because I omit the proof, but the proof is to just take the manifold atlas and make some things with normal bundles to these surfaces and define the M action, etc. It's technical, but well, there's my paper with Vicente Muniz and Juan Ángel in International Mathematics Research Notices, where everything is written in detail. But anyway, you can do something like that. And then what we get the following. So let X omega be, it's X, sorry for the misprint. Let X be a symplectic 4 manifold with symplectic surfaces di intersecting transversally and positively, and coefficients mi such that they are mutually prime if their surfaces intersect. Then there is a smooth symplectic orbifold structure on X. So we get an orbifold structure by distorting the smooth structure. And this still is somehow, you can, just looking at this slide, you can imagine that it may be true. And again, it's a local calculation with compatible Darboux charts, and certainly it's quite complicated. So when we were working on this paper with Vicente said that our colleagues will be thankful for us that we worked out all these details. I don't know, but maybe it's true. Anyway, so this is our simplest case. And now how to construct a non-smooth orbifold. This is much more difficult. And this was done by Vicente. The theorem which he proved was as follows, that let X be a cyclic orbifold with a set of singular isolated points. So you have a true orbifold, but then with singular points and also with embedded orbismooth curve. Orbismooth, it means that, I don't want to details of this, but intersecting nicely. Nicely, it means exactly that locally this is Z1, 0 and 0, Z2. So intersecting nicely. Take arbitrary, this is very nice. Take arbitrarily MI only with this condition on usually primeness. And then there exists a Kähler orbifold structure. So you can put a Kähler structure on this with isotropy surfaces di of these multiplicities and singular points of this multiplicity. And so for us it was very important that we can begin with something, then take arbitrary embedded orbismooth curves, and then just there's the construction a bit resembling previous, but much more technically complicated, and then you can get an orbifold, true Kähler orbifold structure, and it is enough for our purposes. So Seifert bundles. So just maybe I will recall that we started our considerations with Booth-Vivank bundles. Instead of Booth-Vivank bundles, we want to have a more general object Seifert bundle. So formal definition is as on the slide. So you just adapt the usual definition of a bundle to isotropy, to have isotropy subgroup. So I won't even read this because it's easy on one hand. Yes, you take the definition of the fiber bundle and make and adjust it to have this ZM action, and then you have a Seifert bundle oriented over certain X and didn't get oriented fragment. And so you see that then you get a smooth S1 action on a continuous and a continuous map, such that in each orbifold sharp you get this compatibility condition with the action of the cyclic group ZM. Now, if you want to construct Seifert bundle, so our general aim is to take a Kähler orbifold and construct and make a procedure to construct Seifert bundle. So we need some condition on local invariance of X. This is written here, but I wouldn't like to somehow to go too much into technical details. But then what you should fix, what this is somehow again a miracle. So you take a orbifold X, you take the isolated singular points P, and you have your DI, so embedded surfaces or complex curves, and with multiplicities MI. What I've written is a tradition to call this a branch divisor, and delta you write it this way. But for us, it's just an information that we have a pattern of surfaces DI and with multiplicities MI, so the isotropic group acts trivially on this DI. And so for each point X with multiplicities and D and 1 times, we have an adaptive chart, etc., etc. All this which you usually do to work with orbifolds. And so, but now recall again our toy construction, Booth-Vivank vibration. For Booth-Vivank vibration, if you wanted to get it, you just say, okay, take a symplectic Kähler form, take a homology class, of course assume that it is integral, and then take the corresponding circle bundle. That's all. Here you need quite sophisticated condition. So you also start with Seifert bundle. It's our analog of Booth-Vivank vibration of just circle bundle, yes. But you have stabilizer in S1 because the action is not free. So at any point you have a fiber bundle of the form M divided by this S1. And then you take the quotient, but then because you have this isotropy L in S1, and you have the quotient, you have a true manifold. But then associate a true circle bundle with the first term class C1, and then just take this one. This is not integral cohomology class anymore, but it is rational. It is a rational cohomology class. This is the first term class of a Seifert bundle. And then I would say that in some sense you get the same. So now your condition is more complicated. You need to take C1 of this form, which is rational, but you gain what you gain. You gain a lot of flexibility, which you will see in a moment. A lot of flexibility. What is the flexibility? So what is the theorem? It is the theorem of myself and move and descent. So let X be cyclic for orbifold with a complex structure and take this pattern of complex curves in X, which intersect transversally. Of course, take these multiplicities. You take it an arbitrary way as you want. And then suppose that there are given local invariants for each di and for each I singular point. You need some technical compatibility conditions, which I don't want to discuss. And then choose any integers bi between 0 and mi, only with the property that for local invariants, that they are congruent modulo mi. And let B be a complex bundle. Just take a complex bundle over X. But then there exists a Seifert bundle with a given local invariance and with first orbifold German class of this form. C1 is just C1 of B, or your initial fiber bundle, but then with this extra term. And this extra term gives you what you want, because you have a lot of flexibility taking DI, taking BI, and taking MI. And moreover, if X is a Kähler orbifold, and if C1 is the orbifold Kähler form, then M is Sasakian. So this is what is the most, I think the most important thing that we understood, that there's enough flexibility to solve problems. So all this, unfortunately, I'm very sorry for this so technical and so long description of orbifolds. But otherwise it will be even worse. So comparison. Again, you see, this would be one vibration, easy. But then, if you take your orbifolds, you have extra invariant. X, P, branch divisor, surfaces, conditions on Mi, and but take this one, C1. We can gain more flexibility. One wants to choose local invariants in arbitrary way, say, in quotation, ensuring, however, which is also technically difficult, ensuring, however, that when you get your Cm, it will represent the Kähler form, which is not, from this construction, it is not here. It is really sophisticated. But then, final step. Finally, I will introduce the object. At the very end of my talk, I will introduce the object which was somehow investigated. These are Smale-Barden manifolds. The first interesting dimension. The first interesting dimension is Riemannian contact geometry is 5. So because in dimension 3 it's poor. So there are always on in 3-dimensional manifolds you only have a contact structure, and then it's nothing very special. But here you have a Smale-Barden manifolds. So by definition, a 5-dimensional simply connected manifold is called Smale-Barden manifold. This manifold is also unusual, but it's, for example, I guess Stefan would say much better about such things. That these manifolds are classified by their second homology group. It's very surprising, and Barden invariant. because in general, of course, it's not possible to classify simply connected smooth manifolds by pure homotopic terms. But here, yes, you can. So it's these are all invariants up to diffeomorphism, which describe 5-dimensional simply connected manifolds. So what you should do? You should take the second homology group, it's Sapelian group. So because it's Sapelian, you take this non-torsion part, ZK, and you have torsion part. This torsion part is written in this way. And then, of course, the second Betti number will be K. And I of M, this is a Barden invariant. This is the smallest integer, such that there exists a cohomology class with Stiefel-Whitney class evaluated on alpha, not non-zero. And alpha must have order 2 to power j. Then this particular number is called a Barden invariant. And then this is a full set of invariants up to diffeomorphism of simply connected 5 manifolds. And so Boyer and Galitsky, in fact, first asked this question. So can you somehow describe geometry via these invariants? This is very fascinating. And so this is a classification theorem, which I already described. So any Smale-Barden manifold is uniquely determined up to diffeomorphism by this data. And one more thing I need to say is so-called basic cohomology, because our cohomology will be basic because we have a foliation is determined by a rainbow vector field. So differential form is called basic. If these conditions are satisfied, then you can check that this is a differential complex, and then the resulting cohomology is called the basic cohomology. And then finally, I will explain some particular results, samples of our results, and then I will need to introduce a definite Sasakian structure. So you take a characteristic foliation, take this decomposition of a tangent bundle, then take you look at your D as a complex factor bundle, because D, remember that D has this almost complex structure, D eta. And because of that, it's a complex factor bundle, so you have a basic Chern classes. They Chern classes defined as basic cohomology classes. And then the formal definition is that a Sasakian structure is called negative if the first Chern class can be represented by a negative definite 1-1 form, but you can ask why it's symmetric, but you need some extra form determined by this one, and traditionally it's just written in this way. It's a definite 1-1 form, and it is called positive if it can be represented by a positive definite 1-1 form. It is called null if it is 0. And so Boyer and Galitsky asked several questions, and there are several important problems, which, as I said, give some interesting mathematics. So let me formulate some problems of Boyer and Galitsky. So the fundamental is which Smale-Barden manifolds admit Sasakian structures. As I mentioned before, Kohler showed that not all Smale-Barden manifolds admit Sasakian structures. So the question is meaningful and difficult. Are there Smale-Barden manifolds which admit K-contact but do not admit Sasakian structure? Which simply connected rational homology spheres admit Sasakian structures? Weaker, but interesting, which simply connected rational homology spheres and both admit both positive and negative Sasakian structures, and determine which this connected sum admits a negative Sasakian structure, admits when admits no Sasakian structure. And this I will present a sample. Just this paper is somehow, it's easy to explain, so I take a sample of results with Vicente and Matthias Schipp. So these were questions which we of Boyer and Galitsky, and we give complete answers to questions 4 and 5. So we proved theorem 1, any simply connected rational homology sphere admitting positive Sasakian structure admits also a negative Sasakian structure. So we answer in full to this question. And theorem 2, any connected sum of this type admits negative Sasakian structure. So this is a complete answer, obtained by methods which I have explained. So these results were obtained by introducing this new, somehow, theory of complex orbifolds of a particular type. Then maybe some small context, because of course the name of Kohler should be here mentioned. So the most important thing was that for rational homotopy sphere, Kohler showed that there are rational homology sphere admits a positive Sasakian structure only if M is spin and H2 of M is one of the following. So only this group can be realized, and there is some condition that something should be not divisible by 30. So conversely, all these cases do occur. So if you now want to have something negative, you take this one and check if there are negative. And the theorem of Kohler was also very important that if M is Sasakian with a positive Sasakian structure, then a positive Ricci curvature metric on X can be lifted to a positive Ricci curvature metric or Einstein metric on M. Moreover, the lifted matrix is also Sasakian, so it is Sasakian Einstein. So it shows this path which I was talking about, that this is a tool to construct Einstein matrix, and the first result in this direction was made by Kohler.
What is X?
Where?
X, the second theorem. What it is?
X is a Kähler orbifold. Or in case of, yes, a Kähler orbifold. X is a base. Because, you know, all the time you should keep in mind the Struckimbira theorem, that you have this analog of fiber bundle, you have a Seifert bundle. So you take all this X, all the time X is the base of the orbi bundle. And so, well, maybe I'll skip this. So, and then let us think what we should do. So if you want to answer our question 4 of Boyer and Galinsky, so we need to get some Sasakian structure for particular type, or the particular type of Seifert particular type of Smale-Barden manifold. So you need to construct a manifold with B2 of M equals 0 and torsion groups in this second homology as in Kohler's theorem, and with a negative Sasakian structure. So it's a problem, yes? If you want to answer in positive to Boyer-Galinsky problem, you need just to make this construction, and it's constructed. You should do it by hand. And then what is the general scheme of the proof of this theory that we proved? So it was, first of all, remember that there is a quasi-regular Sasakian structure, which is always arises from Seifert bundle because of Struckimbira. There is a method which we proved with Vicente of Kohler type, calculating the second, not only the second, but cohomology of MZ from the data H of XZ, and in particular to calculate H2 of MZ. While I stress that it is a Kohler type method, but we cannot use Kohler result directly because Kohler used only smooth orbifolds. So the singularities are particular type, and we need to gain enough flexibility. We need a lot of singularities. And so, but we managed to do this. So we calculated cohomology in this way, and then if you have the tool to calculate cohomology, then you have construct a Kähler orbifold. There is, of course, now you need to construct it physically, and Seifert bundle also you need to construct it. And worse, you need to have this with prescribed second B2. We need to prescribe torsion in homology, and which I completely won't explain. You need to calculate pi1, the second, to ensure that your manifold is simply connected. And this calculation is also non-trivial because you need to work with so-called orbifold fundamental groups, where loops are around your singularities. So it's a lot. But then if you imagine that, and you believe me that I could do it with Vicente, then you can do all this.
And then you get either rational homologous field or this connected sum. And of course, final step, you need to express in these terms the negativity condition and check its compatibility with other data. So it's a lot. But so the final theorem, because my time is over, in fact, I will take that here, especially my colleague Matthias should somehow make a lot of contributions because he's an algebraic geometer and he helped us to understand this thing, find the right singular surfaces. So your final step in construction, you should I will skip also the calculations of cohomology, but the negativity condition, how to calculate it. This you need to take instead of canonical bundle, you need to take a canonical orbifold bundle, which is defined with your branch divisor as well. Then there is a theorem of Boyer and Galitsky, which expresses negativity conditions in case of so-called emptiness of the canonical class. But then you need to use the Nakai-Moshizan criterion for like bundles, and you get what you want. So finally, I will say that we can now, after all this work, we can forget about differential geometry, can forget about topology, and just take concrete algebraic surfaces and use algebraic geometry formulas and you get the result. So that's what I will skip because I need to find the conclusion. So what is the conclusion? The conclusion is the key points of all these constructions to guess what smooth algebraic surface to take, what chain of curves should be taken, and calculate the rest. And the flexibility is ensured by the choice of the invariant. Remember that we had a lot of flexibility taking local invariants, bi, mi, and so on and so on. And then it's quite elementary say calculations with numbers, but only if you somehow get all this work. And so, example of a choice. If you want to realize, because there are a lot of realization cohomology, but one homology, it's this one, Z2 to 2 the nth power. Then the algebraic surface you should take is a Hirzebruch surface. The chain, it's just one curve, infinity section of the Hirzebruch surface, and you should blow down this curve blow down your surface along this curve, and then your branch divisor should be defined this way. These numbers then should be pair co-prime, etc., etc. But these are just number theoretic, relations. These formulas which you need to use. This junction formula, etc. All these formulas from algebraic geometry. So, and I just because it was written in my abstract, but I did not explain this because the method is the same, but the calculations are much more complicated because you need to take K3 surfaces instead of Hirzebruch surfaces. There was a lot of work with that. But finally, some references. So just to mention all my friends from Spain, which were somehow participated in the project. So these are Marisa Fernandez, Juan Angel, and Vicente, and Alejandro. So, and finally, this Matthias Schutt, because he's German, so I didn't introduce him before, but now he did a lot of work in algebraic geometry to do all this stuff. So thank you very much for your attention. I think that I didn't run out.
Well, thank you very much for your interesting, deep, and broad talk and the crash course in differential geometry in algebraic topology of manifolds. Okay.
I assume I speak loud enough, but I'm not used to such a big auditorium, you know. This is management department. Okay, so, yeah, any questions?
Yes.
I would like to ask you the question because in the examples you mentioned at the beginning of the lecture, I see that there is, you can construct something like two foliations. First, defined by the characteristic field, and the other complementary using steps. Can you say if anything is now about the existence of such speaking in more general cases?
Unfortunately not. If you somehow look at what I was doing,
it is quite specific. It is quite specific. So I would say that basically what I wanted to understand is flexibility of these orbifolds because it worked, but then I didn't try to generalize it in any way. It's somehow I think it would be a different question. Just maybe interesting, but I think it would not somehow correspond to this stuff.
More questions? Go.
Yeah, my question is, what can we say about possible fundamental groups of compact Sasakian manifolds? Do you know anything in general?
let me answer maybe in more detail. Of course, do you hear me? This question for Sasakian manifold is considered in the literature as basically very non-trivial. There is a notion of Sasaki group. It means a fundamental group of Sasakian manifold. And somehow it is analog, the odd-dimensional analog of what is going on in Kähler geometry. It's a famous problem that what groups can be realized as fundamental groups of Kähler manifolds, which is, as far as I know, is not solved. And for Sasakian manifolds, this also is not solved. But there is a conjecture. The conjecture is that Sasakian groups are Kähler groups. So any group which could be realized as a group, fundamental group of Sasakian manifold is actually a Kähler group. And well, some very weak explanation of this is because it's just, you can think about it as a separate bundle of a Kähler manifold. But the problem is that if you don't know what to do with Kähler, then you also don't know what to do. I think a lot about this, but I have no any clues although I think for many years. So, but I have no idea. But there is conjecture, and the worst thing with this is that all Sasakian manifolds which you have at hand, they do satisfy this property. So any Sasakian group is Kähler. There is a theorem, I guess by Chen or something like that. But it's only about Sasakian manifolds which you know. But if you don't know, you can do nothing, I think.
One more question, please. No more questions. So I think it's time for lunch. Thank you very much.